Now that we have reviewed conventional petroleum data analysis methods, we move into the next stage, current methods in future-oriented analysis, especially digital oilfield concepts and machine learning. This slide introduces the digital oilfield concept as a measure-calculate control cycle operating frequently enough to maintain optimal operating conditions. It also highlights massive data and machine learning. This is a fascinating shift in petroleum engineering. Traditionally, engineers collected data, analyzed them periodically, and then made decisions. In a digital oil field, data may be acquired in near real time, processed automatically, interpreted quickly, and translated into actions much faster. In conclusion, the oil field is becoming more like an intelligent system. Sensors measure. Algorithms analyze. Engineers decide. Control systems adjust. This does not eliminate engineers, it makes engineering more data-rich, faster, and potentially more proactive. This slide defines machine learning as a branch of artificial intelligence and computer science that uses data and algorithms to imitate the way humans learn, gradually improving accuracy. In petroleum engineering, machine learning is exciting because our field generates large, diverse, and often complex datasets. Traditional workflows can be slow and labor-intensive, especially when the relationships between variables are nonlinear. Machine learning gives us a way to recognize patterns, make predictions, classify data, and accelerate workflows, but I also want to emphasize balance. Machine learning is powerful, but it is not a replacement for physics and domain knowledge. In petroleum engineering, the best results usually come when AI is guided by engineering understanding. This slide discusses semantic segmentation and shows how ideas from computer vision can be applied to seismic interpretation. The goal is to assign each pixel or region to an object class and delineate boundaries. This is a wonderful example of cross-disciplinary innovation. A method developed for recognizing cars, roads, or animals in ordinary images can be adapted to recognize faults, channels, salt bodies, or seismic facies in subsurface data. That is one of the most exciting things about modern petroleum engineering. We borrow tools from other fields and adapt them for subsurface problems. This slide describes an example where a model was trained using the Atom Optimizer on 4,000 image patches, with 10% used for validation, trained for 25 epochs with early stopping, and the best models saved for prediction. This is useful for students because it makes machine learning more concrete. Instead of just saying AI can help seismic interpretation, the slide shows a real workflow: collect training data, split data into training and validation sets, train the model, monitor performance, stop training when appropriate, and then apply the model to new data. This shows that machine learning is not magic. It is a structured engineering workflow. This slide notes that the machine learning model can provide results nearly as good as a geoscientist. That is a very interesting statement. I would explain again carefully. The point is not that AI replaces the geoscientist. The point is that AI can accelerate interpretation, reduce repetitive manual work, and help screen large datasets rapidly. The final interpretation still benefits from expert review. So the best way to see AI here is as a collaborator, not a competitor. This slide moves machine learning into drilling and well log analysis. Well log data are especially suitable for machine learning because they are structured, continuous with depth, and often available in large quantities. Machine learning can help classify lithology, estimate missing logs, predict petrophysical properties, identify pay zones, and detect patterns not easily visible to the human eye. This is one reason well log analytics has become a major area for AI applications in petroleum engineering. This slide discusses using machine learning together with geological modeling and well data to support 3D models, while also noting that the biggest challenge is the availability of good well log data, especially early in field development. It also mentions that data-hungry methods like GANs may not be suitable when data are scarce. This is a very important lesson. Data quantity and quality matter. My students often get excited about advanced deep learning models, but in petroleum engineering we frequently work with limited data. So model selection must match data reality. Sometimes a simpler model with strong engineering constraints is better than a sophisticated deep network trained on too little information. This slide shows that machine learning can support traditional type well approaches for production forecasting. This is a practical application. Production forecasting is central to reserves estimation, planning, and economics. If machine learning can improve forecasting speed or capture nonlinear trends better than simple empirical methods, that can be very valuable. But again, it should complement, not blindly replace, reservoir engineering reasoning. This slide compares conventional decline curve analysis methods such as harmonic, hyperbolic, and exponential decline with machine learning-based forecasting. It also notes that time series approaches like ARIMA provide a machine learning flavor and can be effective for production forecasting. This is a good moment to make an interesting teaching point. Petroleum engineering is not about choosing tradition or AI. It is about choosing the right tool for the problem. ARP's decline methods remain useful because they are simple, interpretable, and widely understood. Machine learning methods can add flexibility and predictive power, especially for complicated time series behavior. A good engineer knows how to compare both. This slide shows a simulation model for natural depletion linked with a machine learning model such as an artificial neural network. This is one of the most important modern ideas in reservoir engineering, using simulation-generated data to train machine learning surrogates. Why is that useful? Because full reservoir simulation can be computationally expensive. Once an ML model is trained, it may predict outcomes much faster. This can help in screening, sensitivity analysis, and uncertainty studies. This slide extends the idea to secondary oil recovery prediction. Here, simulation results can be used to train ML models for forecasting oil recovery under water injection or other displacement strategies. This is especially powerful because secondary recovery performance depends on many interacting variables: permeability, porosity, mobility ratio, well placement, injection rate, reservoir connectivity, and more. Machine learning can help approximate these complex relationships rapidly once enough training data exist. The reason ML is attractive is speed. Imagine running hundreds or thousands of full simulation cases to study uncertainty or optimize injection design. That can take a huge amount of time. A trained ML model can act as a proxy model to approximate those results in seconds. This slide links CO2 concepts, simulation models, machine learning, economic analysis, and data generation. This is a very rich and modern workflow. Here the story becomes especially interesting. ER is not only a physics problem. It is also an economic problem. Machine learning can help connect simulation results with cost and performance metrics, allowing engineers to evaluate large scenario spaces more efficiently. This is where petroleum data analysis becomes highly strategic. This slide describes an ANN-based expert system trained on field data to generate artificial well logs, assess hydrocarbon productivity at hypothetical infill locations, and create heat maps of productivity sweet spots when data are insufficient for a rigorous simulation model. This is a powerful example because it shows how AI can fill gaps when field data are sparse. Infill drilling decisions are expensive. If machine learning can help identify sweet spots more quickly, it may improve field development decisions significantly. A great key point is this: in traditional workflows, we often wait until we have enough data to build a rigorous full model. In AI-assisted workflows, we may generate useful early-stage predictions that guide decisions before the dataset becomes complete.